Hello friends, so today we are going to solve the questions from modern physics. These questions are from the year 2023. Total 11 questions we are going to solve today, and all these 11 questions are from the mains only. For the year 2023, this will be the part 1. Sorry, it's part 1, not 2. Part 1. In the subsequent parts, we are going to cover rest of the questions. In the first question, it states that energy levels of a hydrogen atom are shown below. The transition corresponding to emission of shortest wavelength is. So in this case, we have to find out the shortest wavelength, and we already know the relationship between the wavelength as well as energy, because energy levels are given to us, and there is an inverse relationship between the two. Okay. So we can write that our energy E will be equal to hc upon lambda, or we can also represent this energy as delta E, which is change in energy, and reformulate the equation as hc upon delta E. So it means greater will be the energy difference, shorter will be the wavelength. Okay. So from here we can draw an important conclusion that greater the energy difference, which is our delta E, and we can say shorter is the wavelength. Is the wavelength, which is represented as lambda. And we already know the standard formula for energy levels in hydrogen atom, and we are given various energy levels 1, 2, 3 and 4 respectively. We are going to find out E1, E2, E3 and E4. So you can say energy levels in hydrogen atom, we can write formula that E of n is equal to minus 13.6 upon n square electron volt, and value of n is given as 1, 2, 3 and 4. So corresponding to it, we can write that value of n is equal to 1. The energy E1 will be equal to minus 13.6 electron volt. Value of n is equal to 2. Energy at that level is our E2, which will be minus 13.6 upon 4, which will be coming approximately as minus 3.4 electron volt. We have our n is equal to 3, giving us E3 is equal to minus 13.6 upon 9, which will be coming as minus 1.51 electron volt. And finally n is equal to 4, giving us E4 minus 13.6 upon 16, 4 square 16. This will be equal to minus 0.85 electron volt. Now we are going to find out the difference in these energies. So we can say energy difference and first let us find out E4 minus E3, that will be minus 0.85 minus of 1.51. This will be coming as 0.66 electron volt. Next we can find out our E4 and E2, that will be minus 0.85 minus of minus 3.4, giving us 2.55 electron volt. Next is our E3 and E2. E3 and E2, E3 is our minus 1.51 minus of 3.4. This will be giving us 1.89 electron volt. And finally we find out our E3 and E1 is equal to minus 1.1 minus of minus 13.6, which is giving us 12.09 electron volt. So this is our, you can say, highest energy difference, highest delta E. So therefore from n is equal to 3 transitions to n is equal to 1, this will be giving us shortest wavelength. So it means 3 to 1. 3 to 1 is our D, so option second is correct. Next question. It states that the radius of fifth orbit of lithium 2 positive is dash into 10 to the power minus 12 meter. Take radius of hydrogen atom as 0.51 angstrom. So we have to find out radius of lithium ion 2 positive ion for the fifth orbit. And in this case we are going to use directly our, you can say, Bohr radius formula. So we know Bohr radius formula, and which gives us for the nth orbit, its radius is given as our n square divided by, multiplied by a naught and divided by z. And z for our lithium ion 2 positive ion is our 3, and a naught is our radius of hydrogen atom, which is our standard, that is given as 0.015 angstrom. So a naught is our 0.15 into 10 to the power minus 10 meters. We can call also this as Bohr radius. And value of n is equal to 5 because we have to solve it for fifth orbit. So value of n will be equal to 5. Therefore we substitute all the relative values and parameters. We get this as r of 5 is equal to n square will be our 25 multiplied by 0.51 and into 10 to the power minus 10, and z is our 3. So this gives us that r of 5 will be equal to 4.25 into 10 to the power minus 10 meters. So it is, power is given as 10 to the power 12, so we can just adjust the decimal, we get this as r of 5 will be equal to 425 into 10 is power minus 12 meters. So we get this will be equal to 425. Next question. It states that the ratio of the wavelength of spectral lines H alpha, H beta in the Balmer series is x by 20. The value of x is. So we are given that ratio of H alpha and H beta is given, and that ratio is equal to x by 20. From there we are going to find out our value of x. Okay. So we can just directly use our Rydberg formula and you can say substitute specifically it for our Balmer series. So we start with our Rydberg formula. And that gives us 1 upon lambda is equal to r, and initial 2 square minus 1 upon n square. And for our H alpha and H beta, we can write it for H alpha. The value of n is going to start with 3 and it is going to end at 2. Therefore, we can modify a Rydberg formula, that is 1 upon lambda alpha is equal to r, and this becomes 1 by 4 minus 1 upon 9. This gives us r 5 upon 36. And similarly, we can write for our H beta. H beta will be giving us transitioning from 4 up till 2, which gives us our lambda beta is equal to r, and we have 1 upon 4 minus 1 upon 16. This gives us r 3 upon 16. Now we can just find out the ratio, and we have to find out H alpha, H beta. So we can say lambda alpha, lambda beta. This will be giving us r 5 upon 36, and this will be r 3 upon 16. So r and r cancels out, and we can write this as 3 upon 16 multiplied by 36 upon 5, and this goes by 4 and this goes by 9, and we are left with this will be equal to our 27 upon 20. And this ratio, that is our alpha upon beta, which comes out to be 27 upon 20, it is given as x upon 20. So from here we get value of x is equal to 27. Value of x is 27. Next question. It states that the angular momentum for the electron in Bohr's orbital is L. If the electron is assumed to revolve in second orbit of the hydrogen atom, then the change in the angular momentum will be. Okay. So for the Bohr orbit, the angular momentum is given as L, and we have to find out when it is revolving in the second orbit, what will be our change in the angular momentum. And for that, we can use the standard formula for Bohr's quantization of angular momentum. We have our Bohr's quantization of angular momentum which gives us the angular momentum in the nth orbit is equal to n Bohr quantized, and it is sometimes also called as a reduced Planck's constant, and its value is this is also called as our reduced Planck's constant, and that is equal to h upon 2 pi. And we have two orbits given. One is the Bohr orbit and the second one is our second orbit. Therefore, we can write that our for Bohr orbit, value of n will equal to 1, which gives us that our L1 will be equal to our reduced Planck's constant at quantized number. And for second orbit, value of n is equal to 2, which gives us L2 is equal to 2h and reduced Planck's constant. And we have to find out the, and in first case it says that for when n is equal to 1, our angular momentum is given as L. So our L1 is equal to L. And we have to find out the difference, or we can also say that based on this, that our L2 will be equal to 2 times L, because our this Planck's reduced Planck's constant is equal to h. So we get the value of L1 and L2. We can easily find out their change in angular momentum. We can say change in angular momentum, let us call this as delta L. So that will be equal to our L2 minus L1. L2 is our 2L, L1 is our L. So from here we get our delta L is equal to L. So option number 3 is correct. Next question. It states that if 917 angstrom be the lowest wavelength of Lyman series, then the lowest wavelength of the Balmer series will be. So we are given the lowest for Lyman series given. From there we are going to find out value of R, and then that value of R we are going to use in the Balmer series to get the required wavelength. So for that we start with the Rydberg formula. Rydberg formula, it gives us 1 upon lambda is equal to R. We have 1 upon n1 square minus 1 upon n2 square. And we have two series. One is our Lyman. So we can modify our this Rydberg formula for Lyman series. So you can say for Lyman series, please remember here it is mentioning as the lowest wavelength. So lowest wavelength means the difference in energy should be our highest. Okay. Or for Lyman series, we can write that 1 upon lambda Lyman series will be equal to R. We have our L1, sorry, excuse me please. N1 will be equal to 1 and N2 will be equal to infinity. So this becomes 1 upon 1 square minus 1 upon infinity. And this gives us our R, and therefore we can write that our R is equal to 1 upon, it is 917 into 10 to the power minus 10, and this comes as approximately equal to 1.091 into 10 to the power 7 per meter. And in both the cases, please remember that we have to solve it for the lowest wavelength. Okay. So similarly, we can write for Balmer series. Our 1 upon lambda, this is our Balmer series, is equal to R, and this comes as 1 upon 2 square and 1 upon infinity. This gives us R upon 4. Therefore, we can say that our lambda Balmer series will be equal to 4 upon R. Or in this case, we can just 4 upon R, or let me write it here. So from here I can say my 1 upon R will be equal to lambda LS. Okay, so we can directly use the value also. So this comes as 4 multiplied by lambda LS, which gives us 4 into 917, giving us 3668 angstrom. So this is a minimum wavelength is 3668. Next, it states that a monochromatic light is incident on a hydrogen sample in ground state. Hydrogen atom absorbs a fraction of light and subsequently emit radiations of 6 different wavelengths. The frequency of incident light is x into 10 to the power 15 Hz. The value of x is. So here we are given that it is having a, it emits a radiation of 6 different wavelength, but initially it is said that our hydrogen sample is in ground state. So we can say that the excitation of this hydrogen atom is going to start from n is equal to 1, and from there we can just reverse calculate or find out what will be the 6 different stages or levels or transitions that are possible. So we can say that our hydrogen atom is in ground state. That is the value of n is equal to 1. And it says that emits 6 different wavelengths. And from these 6 different wavelengths, we can say that the final value of n will be equal to 4. Okay. So we can say it implies they are excited to n is equal to 4. And in between levels will be also present. For example, we can say that, and we have to remember that there is 6 different wavelengths, or we can also say 6 transitions. And 6 transitions, we can say our 4 to 3, 4 to 2, 4 to 1, and then we have our 3 to 2, 3 to 1, and we have this as 2 to 1. So these are our 6 transitions. And so at least from here we can also draw one important conclusion, that the hydrogen and the incident light is having sufficient energy so that our to excite the atom from N1 to N4. Okay, at least minimum energy that is present with our incident photon. Therefore, we can say that this means that incident photon had enough energy to excite an atom from N1 to N4. Now we can just find out the energy difference between these two levels. Therefore, we can say energy difference that is our E will be equal to 13.6 1 upon 1 square minus 1 upon 4 square, which will be coming as 13.6 into 15 upon 16. So therefore we get energy difference E will be approximately equal to 12.75 electron volt. And we have to find out the frequency. So we can use the relationship between energy and, sorry, not energy, but frequency and energy. Yeah. Okay. So we can say that our E, that is for energy, is equal to H multiplied by frequency, or in terms of lambda also, and that is a Hc upon lambda, that will be giving us a frequency. So from here we can say our frequency is equal to E upon H, which will be giving us 12.75, and we have our 4.25 into 10 to the power minus 15. This frequency is approximately 3 into 10 to the power 15 hertz. But we are given that, let me write the final answer, 3 into 10 to the power 15 hertz. But we are given this is equal to x into 10 to the power 15 hertz. So we make 1:1 comparison. We can say that value of x is equal to 3. Next question. It states that the energy of He helium 1 positive ion is in its first excited state is the ground state energy of a hydrogen atom is minus 13.6 electron volt. So we have to find out the energy of a helium 1 positive ion in its first excited state. Okay. So first excited state means value of n will be equal to 2 for our helium 1 positive ion. And its atomic number, that is our He1 positive, Z is equal to 2. So we can use our standard formula for energy of our, you can say, nth state. Therefore, we can say that energy at nth state, that is our E of n, is equal to minus 13.6 Z square upon n square. And we are given as it as He1 positive. For that, value of Z is equal to 2, and we are given first excited state. So therefore value of n is equal to 2. So we can just substitute them and it will be straightforward, giving us the answer. So we can say value of n is 2, so E of 2 is equal to minus 13.6 multiplied by Z is our 4, state is also our 2 square, and therefore 4 and 4 cancels out. So we get our this is minus 13.6 electron volt. So option 3 is correct. Next question. We are given the radius of second orbit of He1 positive of Bohr's model is R1. And that of fourth orbit of beryllium 3 positive is represented as R2. Now the ratio of R2 by R1 is x is to 1. We have to find out the value of x. One second. Yeah, okay. So here we can use the Bohr radius model, but yeah, we can say Bohr model for radius. Bohr's model, it gives us that our R of n is equal to A naught n square upon Z. We have two models, two compound rather. One is ions, one is helium 1 positive and beryllium 3 positive. Therefore, we can write that for He1 positive, value of Z will be equal to 2 and value of n is equal to 2 because it is given as second orbit. Therefore, we can say that our R1 will be equal to A naught multiplied by n square is our 4 and divided by 2. So this comes as twice A naught. Similarly, we can write for beryllium 3 positive. This gives us value of Z is equal to 4 and value of n is equal to 4 because it is says for the fourth orbit. Therefore, our R2 will be equal to A naught and n square will be over 16. Value of Z is equal to 4. So which gives us this as 4 times A naught. Now we can just find out the ratio. So we get our R2 by R1 will be equal to 4 A naught twice A naught cancels out, 4 goes by 2, so we get this equal to 2:1, and in the question it is written as x:1, so making a comparison we get x is equal to 2. Value of x is equal to 2. Next question. It states that an atom absorbs a photon of wavelength 500 nanometer and emits another photon wavelength of 600 nanometer. The net energy absorbed by the atom in this process is n into 10 to the power minus 4 electron volt. The value of n is, it says that assume the atom is stationary during the absorption and emission process. So we can use the, you can say, the formula that is equal to our relationship between energy and lambda wavelength. So we can say our energy wavelength, and that is our E is equal to hc upon lambda, and in the first case it is absorbing, in the second case it is emitting. Okay, so we can modify and we have to find out the net energy. Net energy will be difference in energy. Therefore we can say that our energy absorbed will be equal to hc upon lambda absorbed, and energy emitted will be equal to hc upon lambda emit. Now we can just find out the difference. So you can see net energy absorbed. Okay, so it clearly mentioned that absorbed will be on the higher side, so we can say net energy absorbed, that is our E, will be equal to E absorb minus E emit. We substitute their respective, we get this hc will be common, we get, sorry, one second, I've written this on the reverse. This will be our emit and this will be our absorb, because the relationship is inverse. So we get this as lambda emit minus 1 upon lambda absorb. We can just substitute the values and we get this as h is our 4.1 into 10 to the power 15. Speed of light is 3 into 10 to the power 8, and this is 1 upon 600 minus 1 upon 500, and this is in nanometer, so we can say 1 upon 10 to the power minus 9, and this will be coming as 1.242 into 10 to the power minus 6, and this will go 5 minus 6 divided by our 3000, which will be equal to minus 4.14 into 10 to the power minus 10 electron volt. And so So we are only interested in magnitude. This negative sign is only signifying the absorbed part. Rest doesn't matter. So therefore we got that our energy is equal to 4.14 into 10 raised to power minus 10, and in the question it is given as n into 10 raised to power minus 4. It is given as n into 10 raised to power minus 4, and so we make this will be giving us that value of n will be equal to, one second, if we convert into 10 to minus 4, this will be coming as 1, 2, 3 and 4, 5 and 6. Oh yeah, my mistake. It is let me correct myself, because this will be coming in joules, so we can just take value of our this H will be over 6.6 into 10 raised to power minus 34 into 3 into 10 raised to power 8, and this corrected. So this will be giving us 6.6 into 10 raised to power minus 20 joules. We have to convert into electron volt. Yeah, minus 20 divided by 1.6 into 10 to the power minus 19 electron volt. Now it will be coming, this will be equal to 4.125 into 10 to the power minus 1 electron volt. That was a big mistake. And we compare this n into 10 to the power minus 4. So obviously we can write this as 4125 into 10 to the power minus 4 and n into 10 to the power minus 4, giving us value of n is equal to 4125. Yes, now it is correct. 4125. Next question. It states that As per the given figure, A, B, C are the first, second and third excited energy level of hydrogen atom respectively. If the ratio of two wavelengths, lambda 1 and lambda 2 is 7 upon 4n, then the value of n will be. So we are given that we are having two wavelengths and A is our first, second as well as third. Okay. So this will be our n is equal to 2, n is equal to 3 and n is equal to 4. Because it is given as the excited energy levels. So we have to find the ratio of two wavelengths. Okay, so first transition is from C to B and the other transition is from B to A. So we can use Rydberg formula for the respective parts. And therefore we can say that our Rydberg formula this gives us 1 upon lambda is equal to r z square 1 upon n1 square minus 1 upon n2 square. So we have two wavelengths, so we can modify this given formula into two parts. First is for our 3 to 2 and that is our lambda 1. So we can say 1 upon lambda 1 is equal to r, value of z will be equal to 1. So this comes as our 1 upon 2 square minus 1 upon 3 square, which will be giving us r into 5 upon 36. And second one is from 4 to 3. From 4 to 3 is the transition. Wavelength is our lambda 2, which gives us our r 1 upon 3 square minus 1 upon 4 square. This will be giving us r into 7 upon 144. Now we have to find the other ratio, lambda 1 upon lambda 2. Lambda 1 upon lambda 2. Ratio lambda 1 upon lambda 2. This will be giving us r 5 upon 36 and r 7 upon 144. Here r and r cancels out. This comes as 7 upon 144 into 5 and this comes as 36. And this will be equal to over 7 upon 20. And the ratio is given to us as 7 upon 4 times n. So we can write that lambda 1 upon lambda 2 is equal to 7 upon 20. It is given as 7 upon 4 times n, which can be written as 7 upon 4 multiplied 5. And so 1:1 comparison, this gives us that the value of n is equal to 5. So value of n will be 5. So this completes all the questions. For the year 2023, first part, and completing 11 questions. Thank you.